In this video, we'll finish up our discussion of section 13.2 by evaluating some limits that we are able to evaluate, talking about some methods that we can use to evaluate, and talking about continuity in this video. So let's begin with this evaluating the limit. The first thing, we said this, and we really didn't mention the why we can do this, but we are guaranteed the continuity of that if we can plug it in. Meaning, with this limit and some theory that, and from Calc 1, and we extend it to this, that if we plug it in and get a number, then that is our answer. As long as we don't have like dividing by 0, taking the square root of a negative, all the normal bad stuff, right? But if I can just plug it in, then great. So this is equal to 3 times 1 times negative 2 over 2 times 1 squared minus negative 2 squared. This will come out, you can work that out. This will be I believe, a 3. If it's not a 3, I believe that you will tell me in an email or a text. But it's from my notes, and I trust it. Right, so that's a 3. The next limit, we have that crazy looking problem. But if I can plug it in, then we're good. Right, so I go equal, and then I'm just plugging in each one. The positive thing has to happen because we can't do, and what I mean by the positive thing is this thing, 0 from the positive side. And the reason is because of right here. I can't think about those variables coming from the negative side, both of them, because if two negative numbers are being added together, they're negative, and then I take a square root, which is a problem. So that's why those zeros are there, but I still can just plug in 0. I get e to the 0. Then on the bottom, I got a minus 1. All right, I hope you didn't write e to the 0 with 0. It is 1 divided by negative 1, which is negative 1. If you are ever doubting this, you're allowed a calculator. Please plug it in and check. It's so frustrating to see anybody put a 0 for that because you literally have a machine that you're allowed to check it if you're unsure. Okay, let's do another one. This one looks absolutely disgusting. But remember, if we can plug it in, we're good. So let's try it. Maybe it'll chill out when we plug stuff in. I got e to the sine of pi times x, that's just 0, plus ln of cosine of, okay, we're going to plug y in here. Okay, plugging in y. I feel like I'm missing my z somewhere in this problem. Nope, there just isn't one. So that's good. Y minus 2, if I plug a 3, I get a 1. So this is just pi. And I think that's it there. Check your everything that we plugged in. Z we don't plug in because there's not a z in our expression. And that's totally fine. Okay, sine of 0 is 0. So e to the 0 is 1. Plus, okay, cosine of pi is negative 1. Uh-oh, and then we have some kind of issue here, right? I think this is supposed to be... I think my notes are messed up somewhere. Let's change this to a 1. Then it works out for us. Let's put a 2 here. Forgive me. Put a 1 there. So this is y minus 1. Otherwise, we have a domain issue. So ln, and then I take cosine of 2 pi. That is 1, not 0. Ln of 1 is 0, leaving us with an answer of 1. So forgive me on that minus 1 there. Should have been a minus 1, not a minus 2. If you understand, if you want to know why it doesn't work with a minus 2, is because I would get a 1 pi, right? Cosine of pi is a negative 1. I can't take the ln of a negative 1, which means we can't go any further. So that's why we need to change it. I want to make sure it works out in this problem because the focus of this is if you can plug the numbers in, then plug them in. If you ran into this where you plugged it in and that didn't work, you could write D and E domain issue. Right, that one is definitely not a manipulation. I don't think issue because that ln would be very hard to work around. Maybe you could manipulate it for L'Hopital's or something. We're not going to waste time on that, but just plug it in. All right. So those are how that work. Those work. You just plug them in, solve, and get an answer. All right. So here I'm going to show you another way to go about this. You're not going to like this way. So I'm going to rewrite the problem here because we're going to write a line of equal signs. All right. And we get x cubed plus y cubed over x squared plus y squared. Please, with all of my being, I am begging you, I am begging you, do not do this. It is not equal to x plus y. I understand you want to do that. I understand that when things cross out, we're extremely happy because things get simpler, but just don't. You can't do that. The plus signs keep us from doing that. Here is another route. I can't plug 0, 0 in straight because I get 0 over 0, but I can change if I want. I have that x squared on the bottom is the same thing as r squared, and you're like, oh no, polar, right? We could pull polar in as long, I can make that replacement as long as I respect the other replacements for polar. So I got x equals r cosine theta and y equals r sine theta, and we're going to plug those in here. So we get the limit, and now we change, okay? Well, as x and y go to 0, so does r. But it's from the positive side because this, if I let them go to 0, right? Well, this is only going to approach the positive side of r there. I hope that makes sense because x squared plus y squared will always be positive, and that's how we come up with r. So it's approaching 0, but only from the positive side. All right, so we make all the proper replacements. We get r cubed cosine cubed theta plus r cubed sine cubed theta, and then the bottom gets just to be r squared. All right, we keep working this out. We get the limit as r approaches 0 on the positive side. I'm going to factor out r cubed, cosine theta cubed plus sine theta cubed, and that's r cubed on the bottom, which means, okay, the limit as r goes to 0 on the positive side, those cancel, and we get just left with, that's an r squared on the bottom, not a cube, right? So we have an r times cosine cubed theta plus sine cubed theta. It won't matter what those go to. Those aren't affected by r, so this actually just goes straight to 0. Because if I plug 0 in for r, for those cosines and sines, as r goes, it doesn't even matter what's going to be inside the cosines and sines. They're bounded, we know that, so they're not going to go off to infinity. What I mean by bounded is cosine is between -1 and +1. Sine is between -1 and +1, which means that when I cube them, there is going to be, I guess they could go off to infinity. We won't think about it too hard here. We're just going to trust the theory of the limit. Trying to think of what thetas maybe would spit that out. The cube is what convinces me maybe it'll get bigger, because if I cube a really small number, 1/2, it's 1/4, it gets smaller. Okay, so yeah, cosine cubed is bounded because cosine is between -1 and 1. So the cube would also be caught between -1 and 1. Same with the sine cubed. Since those are caught between -1 and 1, as r goes to 0, the overall number is going to go to 0. Hope that makes sense for you. All right. We have another method using the same approach. So let's try this out. The way it looks right now, I can't do that, but I can make the replacements. And what's great here is this is going to change everything to polar in one change. So I get the limit as r approaches 0 on the positive side for the same argument. And then I'm going to get r squared times the ln of r squared. Now, right now, if I let r go to 0, we get negative infinity out of here. And then we also will get a positive infinity with the r squared. Too much to tell. We can't see what's going on. I am under one variable, which means if I can make a L'Hopital, then I'm good. And what convinces me that it's going to work is this is going to go to 0 as r goes to 0. And this is going to go to negative infinity, right? So that's an indeterminate form, but it's just not the right indeterminate form for L'Hopital. So I am going to use a trick here. This works a lot. I am going to do ln of r squared on top, and then I'm going to do 1 over r squared on bottom. Notice if I were to flip that back over, I get back. I created that, made that happen. Now, I can use L'Hopital. The limit stays. I haven't taken that. Please do not drop it. I will count off. We get, okay, so that's going to be, we do get a chain rule for this. So it's going to be 1 over r squared times 2r. Right? That is the chain rule. 1 over r squared is the derivative of ln of something. Then I took the derivative of r squared, which is 2r. Right? The bottom becomes, okay, so that's, we get a negative 2 over r to the third. Okay, and then I'm going to simplify that as much as I can. Hopefully it works out for us. All right, so I got, okay, that's going to be 2 over r, and then it's times, and I'm going to flip this one. So we get the limit, shouldn't be an equal sign there in the middle. I don't know where that came from. Yep, that's still good. I double check work. The 2's cancel, I get a negative and an r squared. That is a nice, easy evaluation. If I plug in 0, I get 0. Right, so sometimes switching to polar will work, not always. It's just depends on the x squared, y squareds, and what's left. Like in the example above, right, we had to replace our cubes with these other definitions of our polar formulas. All right, let's talk about continuity for a moment. You'll like this. So how continuity works in 3 dimensions. We have some kind of neighborhood. It's just a space in 2D, right? And we're going to have some point in there. And let's not call that a neighborhood. Let's just call that a surface, right? We have some surface, and we're going to put now what we call neighborhood. Let me actually use the dotted lines here. We're going to get some neighborhood of that point. Right? Usually a circle. That's how they do it. Not always, because we're not going to always have that kind of thing. But we'll call this neighborhood delta. And what that means is very small, right? Very tiny neighborhood. And what we can do, because our surface, for continuity, right, we need the point to exist there, and we also need the surface to limit there in all directions, which means is that if I really wanted to prove continuity, I would need to consider within that neighborhood all paths leading to the point. Just like the definition of a derivative in 2 space, right, or a limit in 2 space, I mean, we have some neighborhood down here, and this is what we call our delta, right? It was like, hey, when you get inside this neighborhood, I can guarantee that you'll be this close to this point, right? That's what that was saying. Now that's what we're saying in 3 dimensions or 2-dimensional plane here, is that when we get really close to the point, I can guarantee that I'll be within that distance. Okay, all that to say, it works that way. If we had to prove continuity, it'd be very difficult because of you have to use this limit definition, and to prove a limit in 3 space, it has to be going from every direction. We're not going to focus on that, thankfully. You're welcome. But we're going to focus on how to determine when a function is continuous a quick way. So you have seen this before back in Calc 1, and maybe even before, but a function is continuous at any point on the region, that space there, for which it is defined. What that means is if I can plug numbers in there, then it is continuous there. That's all that means. If I can plug in things, wherever I can plug things in for these type of functions, it will also be continuous there. So this first function here, x squared plus y squared, that would have to be, if I wanted to make a problem, I would need a 0 on the bottom, which means that would have to be a -1 to cancel with that one. X squared plus y squared is never going to be -1. So this is continuous on all x, y. You could say in R2, right? Continuous, I can pick any x, y I want, plug it in, because I'm never going to get 0 in the denominator there. So we're looking for these same trouble spots. So we just write them down, and then we write down our set. Okay, well, I have that e to the x over y. I know y cannot equal 0. I also know that x has to be greater than or equal to 0. So I need both of those things. So this is continuous on, and then I just write set notation like I did for domain. So all the xy's such that y does not equal 0 and x is greater than or equal to 0. So if I pick any point that satisfies that, I know my function is continuous there. Remember, continuous Continuous means that there's no jump, there's no skip, there's no hole. All right, let's take a look at this next example. These are pretty quick to write down. Let's take a look here. So we have that trouble spot on the bottom. Now, we don't have that plus 1 that we had there a second ago. We just have x squared plus y squared equals 0. Or x squared plus y squared. And the only time, and I just gave it away, that we'd have an issue is if it was equal to 0. Well, since they're both squared, if I plug an x in and a y in and I square them, they're both positive. They're not going to cancel each other out ever. So the only point that this is true is the point 0, 0. That's the only point that would make that equation true. So for my continuity, or domain in this case, it's continuous on all xy's such that, and we write it this way, xy does not equal 0, 0. So we have any number we want, we can plug in, except for 0, 0, and I know my function is also continuous at this point. What that means, no jumps, no skips, no holes, right? Those are the type of functions we like to do calculus on, right? No jumps, no skips, right? We need continuous, nice, pretty functions. Okay, this example here. Okay, it says find the set of coordinate pairs where the function is continuous. Okay, so let's take our denominator. This x squared plus y squared plus z squared minus 4 must be greater than 0. It can't even be 0 here. Actually, it can be less than 0. It just can't be 0. Hope you followed that. I almost wanted to put a greater than or less than, but it just can't be 0. So that means that it's x squared plus y squared plus z squared equals 4. So as long as that doesn't equal 4, right, we're good. So this is continuous on the set xy such that x squared plus y squared plus z squared does not equal 4. So continuous on all those points such that's not true. Now, hopefully you know what that is. That's a sphere of radius 2. So you get all of 3 space except for that sphere. You can pick any of those points, x, y, and z, in 3 space, except for this point on the sphere. It can be inside the sphere, it can be outside the sphere. Those will work in this function, except for that sphere. All right, I'm going to do one more problem here. This is the squeeze theorem. I told you earlier that we would use the squeeze theorem to evaluate. I'm not going to review much of the squeeze theorem. If you'd like, just YouTube it. If you need help on understanding what that thing is, you can reach out to me. The best way, what I'm doing when you guys do that, is I'm just looking for videos by Googling squeeze theorem. If you want to try that first, and sometimes those are hard to find, I get that. If that's what's happening to you, please hit me up in text or email and give me a bit of time, and I can try to find you some videos. We're going to apply it here in 3 space with the limit of this surface. And we're going to work up, I'm going to do a bunch of algebra, and then I'll show you why this works out. You're not going to see a lot of these. I won't test on this. I don't think ever. Maybe a bonus problem if I did put it on there. I would like you to work the homework problem or 2 that does this. This is a good thing to know. Just not what I'm fully focused on. So let's give it a go. We got 5x squared y over x squared plus y squared. And what we're going to think about for this is we're almost all positive except for that y. And we're going to work down to that. So I'm going to take the absolute value of this, and this is going to make sense here in a moment. Right? This is actually equal to 5x squared doesn't need absolute value, but y does. And x squared plus y squared also does not need absolute value because it's always positive. Okay, so I'm going to use some logic here to work our way up into our argument. I know that 5x squared divided by x squared is equal to 5, right? Because that's a 1. So what this tells me is that 5x squared plus anything in the denominator that's positive is going to be less than or equal to 5, because y could be 0. That's the or equal to. But if the denominator gets bigger, consider this. 1/3, if I make it go up by 1, 1/4. It got smaller. If I go up to 1/5, it got smaller again, right? If I make the denominator bigger, it gets smaller. That's why I get this, because I know that when I just do x squareds with a 5, I get a 5. So if I add something in my denominator, it gets smaller. So it has to be less than what it was. Okay, I am going to now, I typically can't multiply by something on both sides of an inequality unless I know its sign. Because if it's positive, I don't flip the inequality. And then that's the one rule for inequalities, if you've forgotten. If I multiply both sides by a negative, the inequality flips. Well, I'm going to multiply both sides by a positive and keep my inequality. If I did y, I actually can't do just y because I don't know what the sign of y is. But I can do the absolute value of y because I know it's going to be 0 or positive. I also know that this is less than or equal to 0. Or that's greater than or equal to 0, meaning 0 is less than that. It's always positive. We know that. We can see it. All the squares and the absolute value. Okay, so consider now, whoa, it zoomed in on me, the limit as xy approaches 0, 0 of 0. Well, that's 0, right? No surprise, that's this side. That's what I'm doing, right? And then also consider the limit as xy goes to 0, 0 of 5 times y. Well, that's going to be 0. These are both true, right? Let's highlight these because they're going to be really important argument. Let me do this much faster. This is equal to 0. And this, I just wanted to make sure you can differentiate the two. There are two things happening here. And I also know this, those three things together, excuse me, I'm going to cough. Sorry. All right, so this tells me now that the limit as xy approaches 0, 0 of that thing that is stuck in between 5x squared, because I know it's always going to be between these two functions. That's what that top blue cloud says, right? Stuck between those. So if it's always stuck between those two, and the two things it's stuck between goes to 0, that means that thing itself has to go to 0. Now, we didn't answer the question, though. The big difference about what we answered and what was the problem is there isn't absolute value on that y. Okay, now this is going to be a continuity thing. I can actually take that y, and I can take it and, let me show you, move it out. So it can become this. Nothing changes with that. X squared plus y squared. Now, back from Calc 1, and maybe you don't remember this, and that's okay. This is a weird idea. Since the function absolute value, right? The function of absolute value is continuous, then we can actually take that absolute value and extend it all the way out, right? So I know, let me write a few things actually. Let me change something. I want this to flow really well. So let me, all right. So this thing, we agree that 0 is equal to the limit, and I'm not going to write all that in, but 5x squared of y over x squared plus y squared. And that is equal to this, right? We didn't change anything. So 0 equals that limit. We proved that. We showed it using the squeeze theorem. Now we're saying the absolute value can be extended out. And then using Calc 1, we can actually take that absolute value and extend it to the very outside of our limit because it's continuous. So 0, 0. Then this goes on the inside. X squared plus y squared. Well, the absolute value doesn't mean anything in that point. So following that chain of equal sign, I have the limit as xy goes to 0, 0 of 5x squared y over x squared plus y squared is equal to 0. There's no other option, right? So we proved the absolute value case. So let's do a recap of our problem because this one's a bit difficult to follow. So this is a trick knowing too to try. We took the argument of my limit and we put it in absolute value. That's what we did first. Then we worked it down and simplified as far as we could because we want to make our expression. Now we're focusing on this part that doesn't have the y, right? That's what we were trying to focus and make it bounded by something. Well, we started with this. Okay, I know that's 5. So if I add the y squared on the bottom, I know the whole thing has to be less than 5. That's the idea that kind of unlocked the problem for us. I have that. Now that I know that the absolute value of y is positive, I can multiply both sides and keep my inequality. That's how I created this super important inequality here that shows that that middle part is definitely always positive or 0. And the right-hand side, it's that the middle part is always less than 5 times the absolute value of y. Well, since that's true, that means that middle part, this part, is caught between 0 and 5 absolute value y. Always. It's caught in between. So that means that if 0 goes to 0, well, it is 0, and this goes to 0 at a certain point, and the function that was caught between them is always caught between them, and they're both 0, there's nowhere to be besides 0. So that tells me that the limit of this function that has that absolute value is 0. But that's not what we're evaluating. So we use this idea, okay, we wrote down just what we just found. And then we extended the absolute value to the outside of the argument here because that doesn't change the number. Just consider it, right? It doesn't change anything for us. Then by Calc 1 and using the idea of continuity, that absolute value can be taken to the outside of the limit. Well, if the absolute value of a limit is equal to 0, then the limit itself is equal to 0, right? It can't be anything else. The absolute value wouldn't change anything. Hence, we have our final answer that that limit is equal to 0. I do want to warn you, and I want to make sure it's in video. On my test, if you try to show a limit and you just wrote right here and you put zeros and that's equal to 0, and like this is the line you wrote, and you put a bunch of x's and one, you just put 0 and you wrote this. I always get this. I always get 2 or 3 people, and they'll do this, right, with their and say that's equal to that, and then they're like, oh, cool. And then you would think, and maybe some of you guys still think that you should get credit because you got the right answer. I don't give any credit for this. Like that, I give you the credit. I have a basic grade line. I determine a point system, and then I pick a minimum point system that if you tried the problem, you get the minimum. For instance, let's say there are 10 points for a problem. If you wrote anything down, I may give you 2 or 3. If you wrote anything down, that this would get that, I guess. But you would get 0 points after the fact of getting points for writing literally something down. With that as well, do not leave my problems blank. Write something down. Try as much as you can. Just because you can't get to the final part doesn't mean I can't find parts to give you credit. You say anything true, I'm going to figure out a way to give you some partial. I'm also going to give you 2 or 3 points just for trying it and not leaving it blank. If you leave it blank, it's a 0 for that problem. Do the problem, you may get 20%, 30% of the points. That may save you from failing to passing. Try everything. Write something that makes sense down.